adjusted this microphone appropriately?
I think it probably will be okay. Okay. Yeah, I don't want to go straight into it anyway. So.
Yeah, they got it set up pretty high gain on here. With that spotlight, the spotlights are very bright in this room. Do you want the light, the house lights down?
I think that's because I have code on, so it's going to be something.
You have code on black.
But this projector is not very powerful. So.
Yeah. Okay. Good. Great. So thanks for joining us for the differentiable programming session. We're going to first differentiate all the things with Mike Innes. Here he is.
Thank you. Hello. Let me just turn this on. Are we good on audio, video? Okay, cool. So this is a talk about Flux, which is a machine learning library, which hopefully some of you have heard of. If you haven't heard of it, this talk might be confusing. I'm sorry about that. It's also a talk about Zygote, which is the new automatic differentiation tool, which we're now bringing into Flux officially. So I announced Zygote last year at JuliaCon and probably said something like, we'll have a new AD in Flux in the next few weeks or something. It's been a little bit longer than that, mainly for good reasons, mainly just for the reason that we got distracted, which is a good reason. We found that there's lots of interesting things that you can do with Zygote in various different areas, and we're going to see some talks about some of those things. So we've been focusing on making some interesting applications work rather than kind of bringing things into Flux. But that's all going to change. So as of today, you can add the Zygote branch of Flux and try Flux with Zygote as the default AD. And there aren't too many changes. The idea is to not be to be kind of backwards compatible with code you already have. But over the course of the next few months, based on having Zygote, we're going to be making quite a few nice API changes and fixes and tweaks to Flux itself now that we have this kind of new technology to make things a lot nicer. So right, let's jump into what that's going to look like. So probably the least interesting thing that Zygote does as an AD changes is that it's fairly fast. If we look at kind of a common way of measuring performance in AD, it's called AD overhead. So if you have something like an addition or a plus or some other basic operation, how much time is spent manipulating AD data structures or running your interpreter or doing dispatch as opposed to doing actual numerical work. And in, say, Python, and also in Flux's current tracker AD, you're limited to about a microsecond of kind of AD overhead of extra work per operation, just because you're running through this interpreter. So Zygote, because it gets rid of that interpreter, because it's in the compiler, gets us down to, in the cases I've tried, it's kind of more like 20 to 50 nanoseconds. So that means that you can now run, rather than having to run huge batch convolutions, you can now run much smaller and more fine-grained models. Not scalar models quite yet. We can run scalar code, but it will make it about 30 to 50 times slower. But it's not 1,000 times slower, so that's something, right? So that's one thing. But really the more interesting thing is that Zygote changes a lot about the way that Flux looks and how it feels to use. So let's have a look at that. If you use Flux's AD now, one of your best friends is going to be the set of functions called param, where we tell Flux to start tracking something, the tracked array type, and the back function which tells Flux to backpropagate through the bunch of things that you've just done with your variable x. Basically, this is all nonsense and we want to get rid of it. It's still kind of a hassle to deal with. It's complicated, it's fiddly, and so we're replacing that with just this one function called gradient. It's a one-function API. This is all you have to do, just call gradient. And this is much, much cleaner. It's more mathematical. It's easier to express nested AD when you're using this. And there are no track types here, so when you're running your program, you won't ever see a tracked real or something like that. You'll just see the integers you're working with, or the tensors you're working with, or whatever that happens to be. This will probably make some of you very, very excited, I hope. If it's not obvious why, let me show you some of the kind of issues we've had with tracked arrays, right? So the thing about tracked arrays is that they're messy in a lot of ways, but as one example of why they're messy, consider the fact that when we have like an array like this, 1, 2, 3, if you do something very simple like mapping the identity function over that, you'll actually get back not a tracked array, but an array, a normal array of several tracked real objects. And this is a huge, huge pain. It causes a lot of bugs and weirdness generally. So getting rid of that is going to be like that's going to prevent, a lot of people from opening issues, the currently open issues on the Flux tracker. Going a bit deeper into that, so I want to show you kind of how deep learning looks without Flux, and that's going to tell you a bit about what Flux means is going to change once Zygote is ready. So I'm just defining a dense layer here by taking two matrices and returning a function that does the usual, linear layer transformation on it. And then chain, which is folding those functions together, those dense functions. But then MLP, which is a chain of two dense layers, as we might use when we're doing MNIST or something like that. And then a dummy input X, which is just going to be a series of random numbers. And calling that, okay, there's our output of a network. Now, how do we get the gradient? Well, just take the gradient. And this is the only thing that's not standard Julia code here, right? Everything else will work in your REPL right now. If you do using Flux or using Zygote, you get the gradient call and it adds this. And the gradient is this struct, this object, which has the same structure as the original model, but contains gradients. So in our original model, we could say, MLP dot, the first layer dot W for our weight matrix, and the gradient struct has the same object, but it's a gradient of that thing. And then finally, we're going to do the gradient descent update step. So if this is all plain Julia, what's Flux doing for you? It might not seem like it's doing very much. So let's talk a bit about that. So one thing it's going to be doing is that this line here, only one very small line in the code, but it actually turns out to be reasonably complicated. So for multiple reasons. So you have things like the gradient descent optimizers that are in, standard machine learning libraries, things like ADAM and RMS prop and normal gradient descent, all these kinds of things. But you also have optimizers like those in optim.jl, things like LFBGS, which we want to support on neural network models, just to see what happens. So actually a lot of work is going to go into Flux and into kind of making this work nicely, especially making it work nicely on TPUs, making it work so that you can do gradients of the optimization process and do like meta optimizers. So that's all stuff that's coming to Flux with like a much more functional interface than we kind of have now, and a much more principled interface. So that's Derek Gandhi, who's done a bunch of work on Flux's optimizers, now refactoring and writing them, and is now looking at rewriting them again, and we're all looking at doing that for Zygote, and that will bring us a lot of nice things. Another thing that we end up doing a lot in Flux is we end up doing things like this, where how do you turn off gradients? Well, at the moment, you have this kind of ugly map leaves of data, which strips away the Flux tracking, the tracked arrays from your model. And then for things like, for dropout and batch norm and so on, you also want to turn those off, so you end up doing test mode. Again, basically nonsense that we want to get rid of. And we can replace this basically, well, firstly, train test mode, you're just taking the gradient, right? So if you're not taking a gradient, then you're in testing mode. There's no tracking, so if you just call your model like I did before on an input, there's no extra overhead from gradients there. It's only when you apply the gradient function that anything happens. But also we can do some nice things, like we can actually define an isTraining function whose adjoint is true when the normal function, the forward pass, is false. So we can now say automatically, like, are we training or not within a layer, yes or no, and then do something smart based on that. So in Dropout, for example, we simply check, are we training? If not, don't do anything. And so this gets rid of some more functions from the Flux API. I'll show an example of that. So defining a dropout layer, here's an input. Define our model, not going to do anything. But then when we take this gradient, we are going to see that some of the gradients have been dropped because of dropout. So that makes things pretty neat. Another thing that comes up a lot is RNNs. So we're obviously providing, and we'll continue to provide, LSTM layers and RNN layers and so on. But RNNs are tricky, right? So when you have an RNN, a loop like this in your model, you end up unrolling it. You have to unroll it manually, or you have to have a for loop to do that. And then you have to decide what kind of a window do you want to backpropagate over. Because if you have a long sequence, you're training car and N over Shakespeare or something, you can't backpropagate over 1 million characters of text. So you end up having to do a lot of complex stuff with Tracker now today and with other frameworks to say, okay, clip the gradient every 5 steps, or just drop the gradient so that you can only backpropagate over short time windows. And then maybe you want to do something more complex, like you want to say, okay, actually have a sliding window where we always backpropagate over the last 5 time steps rather than doing chunks of 5 separate at a time. So traditionally, we've had APIs for that, like truncate and various other bits of computational graph munging, where you have access to the computational graph of your program and you kind of manipulate it. Again, more nonsense we want to get rid of. We never want to have a computational graph. It's not something Zygote has any concept of, so we can't do it this way. But we can actually do it in a nicer way, which is something like this. So if you're writing an LSTM, and imagine the layer wasn't recurrent, you just have a for loop over your the items of data that you have, and then you take a gradient, and then you call the loss of your model on the data and whatever output you're expecting. The only change we have here in this snippet is the record function. And the record function is the primitive that allows us to do backpropagation through time. So in this case, we're saying, well, do backpropagation through time over the last 4 iterations or 5 iterations of this for loop, the 5 pieces of that sequence, and do it with an overlap of 2. So do chunks 5 at a time, but 2 overlapping in each case. And so that gives you fine-grained control over what kind of backpropagation through the time you're doing, and it makes it completely orthogonal to the definition of your model. So you can have a sequence of 3 LSTMs or a more complex, a kind of RNN structure, and it will always work with the same interface. So that's something we can only do when we have Zygote's model of AD. Another thing which is related, and again, this is more work by Derek Andy. So if you're using the CUDA interface right now, it's actually very similar to the tracked array interface. You end up having to convert your data onto the GPU to move it to the GPU explicitly. Then you have a separate CUDA type, which is not a normal array type, and you have to collect it to move it back to the CPU. And again, this causes all kinds of issues. People often end up doing things like combining GPU arrays with CPU arrays, and then that breaks because that's not a well-defined operation. So again, we get rid of this, and we're actually replacing it with more kind of compiler technology like we have for Zygote, where we actually just have a context that says, in this context, execute all of these operations in the GPU. And we can have things here like run on this device, or run on these 2 devices, or run on this stream. So it makes a lot of the API interactions we have for things like parallelism and CUDA streams much simpler. And it's just very hard to get wrong. There's no CUDA arrays here. There's just normal arrays. You define array W and define array B, and you multiply them. But that multiplication will happen on the GPU. So for example, if you have a more complex model, instead of having to move this model to the GPU and then move your data to the GPU, we literally just say take this gradient on the GPU, and it's about the computation you're doing, not the data you have. And this opens up also some nice things in terms of things like Flux.train doing things on the GPU automatically for you, because you never have to worry about moving things to and from the GPU. So we can do that kind of thing much more automatically. So that's a lot more experimental at the moment, but we can do some interesting things with that. Other things you might have seen and heard of around the conference. So I've given a few talks on kind of doing differentiable programming with Zygote, and various things we can do around, things like taking a very complex simulation of something like a trebuchet, where we're handling the arm of the trebuchet and the force of gravity and the mass that we're throwing being attached to the string and so on. All of this is a complex simulation that we can actually differentiate through and optimize. So I've talked a lot about that in the past. I'm not going to go into loads of detail because we have other things coming up and other talks in the conference, but just to talk a little bit about kind of the Flux side and the API side. So right now, if you want to do this with Tracker, we actually have a package called diffie-flux, and we have a separate set of APIs that you have to use for finding derivatives and for specifying the kind of derivatives you want. So again, you can guess what's coming now. This is nonsense we want to get rid of, and the idea is to replace that with just gradient of solve. And so the goal here is that the the API that you use for solving a problem for taking gradient shouldn't be any more than what's in the differential equation stocks plus the gradient function. And so that kind of stuff becomes a lot more intuitive and easier to work with. On top of that, we have some really nice things. So this is a very cool demo, and I don't want to spoil Avik's talk, so you should definitely stick around and see what he's doing with this. But just to give you a very, very brief taster. So this is Ducky Town, and if you've ever been to the Starter Center in MIT, you might have seen this setup, which is basically like a Lego kit for self-driving cars. You set this up with your mats for the roads and so on, and you have these little duck robots that drives around it. So we're actually building things like renderers for this simulation. So you can simulate the Ducky Town environment, and you can build an agent that drives around it. So and we can actually, because we can differentiate through that, we can, if you look at like control problems, then they actually look a lot like RNN problems, like the kind of things you do when you're doing translation and like sequence-to-sequence models. The difference from translation is that this environment is normally a black box. So you can't differentiate through it, which means that you have to do reinforcement learning or something like that. But with Flux now, with these tools, we can actually differentiate through this whole loop, including potentially, if the agent observes the environment through a ray tracer, for example, because it's doing computer vision, you can go through that stuff as well as the physics of the environment and so on. So we can actually do backpropagation through time on these kind of control problems, and this ends up, at least in the cases we've tried, meaning that we can bootstrap these reinforcement learning-like models, these control problems, very, very quickly. So something like Harpole will train in something like 100 times quicker using this. And so we're hoping that we can train things like a Ducky Town self-driving car simulator, an agent, that we can eventually actually run in the Ducky Town environment, for real. And yeah, that's kind of that for me is kind of the future of where ML is, interesting ML is happening, is when you can incorporate the knowledge that you have about the environment into your code and into your models this way. I'll show you one last example. So using this, we can actually add a gradient for PyCall. So we can define a function in Python using PyTorch and define some Julia arrays and then call that function. Okay, we get an output as normal. And then take the gradient. So there you go, easy peasy, an MLP. And we can use this to do things like reusing transformers and so on, things like that people have defined in Python. I'll just show you that you can actually redefine this model. And you'll see you get different results, so it is actually working. And it turns out Python's quite nice to use if you're using it from Julia inside Juno. So yeah, tip there if anyone feels like trying Python. Cool. So yeah, and that's kind of a very simple thing. So this is just one example. We want to do this also for things like, so there's a great project out of MIT recently called Enzyme, which is differentiation of LLVM code. And so we can use this and kind of tricks like those used in cxx.jl potentially to do things like add in a joint for CCall. And then we can kind of you can do a CCall into some Fortran code, and then we actually derive that code via LLVM and then get the gradient of it when you ask for the gradient. So there's lots of really interesting things we can do with this, which haven't really been done before in the AD world. So yeah, that's how Flux is going to change when we add Zygote. It's unusual in that we're mostly just removing all of Flux's features. So yeah, no new features to get excited about, just things you didn't want going away. So yeah, try it out. You don't have to be on 1.3, but if you're on 1.3, you'll get some recent fixes that do improve and make things a lot nicer. Thanks to the compiler team. But yeah, you can try it on, it will work on 1.0 and 1.1 as well. So give it a go, open some issues, and try and build some interesting models. Thank you very much.
So we have plenty of time for questions. Just if you have a question, please use the mic so that it will be on the audio. I should have said that into the mic.
I can repeat the question as well if people want to just throw their hands up. Yep.
Hi, thanks, great talk. I have a question about the gradient, new gradient interface. More specifically, I was wondering, if you're doing something like a generator adversarial network, you can kind of share tape of some subpart of the computation. I was wondering if you have like API to do something like that.
Yeah, absolutely. So we're pretty flexible about, so under the hood, you actually use Zygote to like turn a function into its value that it produced, and also something called VJP, so a vector Jacobian product, which implements kind of the process of going from the gradient of the output to the gradient of the input. And so you can use these and kind of like, if you want to do something more advanced, you can just take those and combine those together in any way that you feel like. So that's how the backpropagation trick that I showed you is implemented. That's actually recording a series of backpropagators for the function you pass it over time, statefully, and then kind of running back through those after 5 steps, for example. And so you can actually, it's sort of, it feels as though like the computational graph approach must be more powerful for doing this stuff, but actually it turns out you can do all of this stuff, with backpropagators, and usually in a much more kind of principled way that kind of respects like, the mathematical form of these things.
Thank you.
I have a question.
Mm-hmm.
So the gradient of a pi call or a c call, could you explain this witchcraft?
So it's pretty simple, right? Let me try and revive my laptop. So we take the adjoint pi call. We're just taking all the arguments, and in this case, so there's actually a slight hack here, which is instead of converting the arguments to numpy arrays when we pi call, we actually convert them to PyTorch arrays instead. But beyond that, we're actually just using the PyTorch API. If you've ever used PyTorch before, you'll recognize this code because it's the same. So we do the pi call and we get y. Y is a PyTorch tensor. Detach that and convert it back to NumPy to bring it back to Julia and show it to the user. But then in the backwards pass, we actually keep y and we propagate that gradient backwards. Again, just using the PyTorch API. Another thing that we're interested in is kind of doing this the other way, like Python to Julia. So for example, there's already, of course, an amazing PyDiffyQ package that wraps Chris's ODE solvers in Julia. So we'd like to have a situation where, a user in PyTorch can actually call those solvers and get the gradient of an ODE or a neural ODE back into Python, but, running in Julia. So that's all, those are all interesting things that we can do with this.
Is there anything you can do with scalar types similar to getting rid of the array to array distinction? Like the current situation with Flux and float 32 versus float 64 versus in the future float 16 is a little bit unfortunate, right?
Yes, that's a good question. So in principle, all we're doing with the CUDA pass is. Oh yeah, sorry. So the question was, can we do? So we have kind of a similar situation with CUDA as we do with floating point types. So things like float 16, float 32, float 64, you kind of end up doing all these same things of saying, okay, convert my model to float 32 or float 16. Also convert my data, because if I don't, then that will fall back to like the generic Julia mapmol, which is 100 times slower than BLAS. So you have to be quite careful. In fact, so it kind of ends up being the same problem. And so what we could do with that in future is to have like a float 16 context where we say, run this whole model in float 16 or something like that. Or, maybe that ends up being an argument to the CUDA pass because that's where it's most important, things like that. So that's another interesting problem, yeah.
One last question?
All right, thank you very much.